Welcome to this short video on the call stack. It's important to understand the call stack for a number of reasons, but in particular there's two different environments where understanding what the call stack is and what it does is important. The first is in embedded systems, where we need to understand the call stack to allow us to debug our programs. And the second is in the security space, where we're considering code hardening techniques, where we're trying to understand what weaknesses our code might have. So it's important for us to understand the call stack in both of these applications. So what is the call stack? Well, to understand that, let's look at some fairly simple code. And in this code, we have a simple function called foo, a single global variable, and some other variables. And what we want to do is understand where the information that is a part of our program exists and how it gets there. So we really have two different categories of storage where we can put information. The first is static memory, which is normally associated with program space, and the second is dynamic memory, which is normally associated with variables. Oftentimes we call that the heap. So let's look at our heap, which is the dynamic memory, and then we have our program memory, which is the static memory. And then let's look at our code and see where each of these different kinds of information go and when. So first, during the compile and link phase, this is not during the run phase, but during the compile and link phase, the program is actually translated from our C code into machine code and placed into program memory. And that shouldn't be too disconcerting, or we should kind of understand that. But also, interestingly enough, our global variables will also be placed in static memory. So in this case, during the compile and link phase, in the static memory, a place is made for global 1, and global 1 becomes the label associated with that piece of data. Then as we compile the function foo into machine code, that machine code is placed also in static memory. Now the actual label foo is a pointer to the very first location associated with that function. Now if we went on and looked further down in program or static memory, we'd see our function main and the machine code associated with that. And that's designed to stay in static memory and not move around, and that is created and put there during our compile and link phase of our process. Now during the run phase of our process, something quite different happens. As we all know, when we run a program, a C program, we start at int main, not at foo. So we go to int main, and as we create variable 1, it is placed into the heap in dynamic memory. And when we hit int variable 2, it is also placed into the heap in the next location in dynamic memory. But that shouldn't feel too unusual. But what is interesting is when we hit the foo function call, we have to store the return address so that when we're done with the function foo and hit its return, we can actually come back to the close location where we called foo. And so that is stored as an address. So in this case, in our heap, we have a data location for variable 1, a data location for variable 2, and the return address for where we called foo, and that is called the stack. Now, when we get to foo and we add int variable 3, we're going to place that on this stack, again in this heap dynamic space, but right after the return address. So variable 1 and variable 2 came to us during the runtime when we executed main, and the foo return came as the function call foo occurred, and now we're going to place variable 3 right after that return address. So this is called the stack, and it holds both local variables and our return addresses. Now the stack pointer is simply for this thread of execution where the next location is where we would store variables. So if just before variable 3, the stack pointer will point to the location in dynamic memory where the next value would be located. After we stored variable 3, the stack pointer would move down to the next location. Now, in addition, we have another value that's being changed, and that's the program counter. The program counter is actually held by the microprocessor itself, and it points where in static memory we're actually executing. So as we execute, we do a machine language execution statement, then we go to the next one, and then we go to the next one, so on. Now a function call, like a function foo, if we were down in the main, in the static memory that held the machine code for main, when we call foo, we would then move up to this memory location. So there's two pieces of information that are important as we execute our code for each task or thread. One is the program counter, which tells us where in memory we're executing, and the stack pointer, which holds the next location for variables. And then again, as we move through the execution, we're going to change the stack pointer as we add variables or function calls, and we're going to change the program counter as we execute our code. Now, one of the questions always becomes, how big is the stack? And the question becomes, it all depends on the number of local variables that we have, plus also the number of function calls. So after variable 3, when we call the foo1 function, we would then store in the next location the return address to return right here where we called foo1, and that's what we call the stack and the stack pointer.